Hi, I'm Shannon Stewart, Senior Data Scientist at the Global Fund to End Modern Slavery. This is part 3 in a video series that I have made to walk you through the model we've created for supply chain data called the Forced Labor Automated Risk Estimator. Our goal with this project is to estimate the risk of forced labor either high or low at the firm level. Some of the features we're using to make this prediction are operational features of the way the business is operating in the supply chain environment. And so, in the previous 2 videos, we went through gathering open source data that pertains to this, and then making clusters of entities so that we can recognize the same single entity within data sets and across data sets. And today we're going to add in a couple of additional features where either the data was sparse to begin with or where we need to compute one of the features. So that's what we're going to start with. One useful characteristic for predicting the risk of forced labor is how many trade partners each given entity has. So for instance, within the same industry, if you computed the whole trade graph for every entity and found that the median number of trade partners was 2, but that there was a small cluster of entities that had 25 or 30 trade partners, we might be able to infer from that, for instance, that one of the entities had assembled its supply chain too hastily and is not capable of adequately overseeing or doing its due diligence on its buyers, which over time could attract suppliers to that buyer that knew that they couldn't withstand the scrutiny of a more engaged buyer. And we've seen specific instances of both kinds of problems depending on the context, but overall I think it's useful to track this as a measure of supply chain entropy and to normalize it within an industry because different products have different levels of complexity. So within this model, we're only comparing supply chain data of garment and textile businesses. So the average complexity of the product should be roughly the same averaged over the whole industry. But for instance, if we were looking at automotive manufacturers, we might expect a higher degree of supply chain entropy to be the norm, but still want to be taking a particularly careful look at those buyers or suppliers that had made an unusually high number of trade relationships, especially if we're time limiting it to, for instance, the last 5 years. And so, this little chunk of code here, beginning on line 211, goes through a way of computing the number of trade partners observed in the data, which we need to do before we completely deduplicate all the clusters, because the way the data is structured, we might, for instance, get trade data that suggests that Intertext received a shipment from XYZ supplier, but that, for instance, in the open apparel registry, they're listed as Zara is working with these suppliers. So all of those sort of need to be merged before the cluster is completely deduplicated. And that's what this little block of code does. I think that one of my ambitions for this project, and the code at this point doesn't do this, but I believe we should be able to add in domestic trade data using e-way bills, which is a record of trucking shipments within India that mirrors the import-export data that we can get from their customs office. The next thing that we're doing before reducing the clusters here is grabbing the longest address. And the reason I'm using the longest address is because if you just open the data that you have and read some of the spreadsheets, typically the more specific and detailed the address, the more likely you are to be able to accurately identify the real location of that firm, as opposed to just, for instance, a province or a country level designator. And so I'm just going by the longest string in the address field for each cluster, and I'm making that the canonical address. And there are going to be instances where that's not the right thing to do, but they're fairly rare. So I have in this data seen instances where the address is, for instance, a narrative description of how to get to the factory, like 3 kilometers past such and such landmark on XYZ road. That happens, but it's relatively rare. And as we kind of go through this and process this information, mistakes like that will end up just becoming blanks in the end. So we need to convert all of these addresses into latitude and longitude coordinates if we don't already have them. And the reason for that is essentially that it's much easier to work with numerical data in a model like this than it is to work with categorical data like addresses. There's no way to relate two addresses to each other that implicates whether they're nearby or far away, for instance, without a little bit of numerical information. And so the next step after we've established a canonical address for each cluster is to do a lookup using the Google Maps API. And this is intended for only suppliers for which we don't already have latitude and longitude information. So all of the firms in the Open Apparel Registry already come with that information. But it's really a minority of the firms that we have in our data set. And so to accomplish this, you're going to have to interact with the Google Maps API. And I will show you what you're looking for. So you go to developers.google.com/maps and go to Get Started, and it'll take you to a dashboard like this. And the first thing that's going to pop up here is a request for a way to build this project. And so you may be going through my code and get stuck at this point because I have not shared my API key with you. And that's because doing so would allow you to bill your project to me personally. And so you're going to have to create a billing account, and using that, you'll be able to get your API key. And then your API key will go here. Oh, sorry. It actually won't. It goes on line 261. So once you've established a billing account, get your API key and insert it on line 261, and then you'll be more ready to go. So this next block of code goes through the Google Maps API and searches each address and saves the results to a JSON file. And then it pulls out the latitude and longitude for that JSON result the best it can. And there's a hierarchy of geographical specificity in the JSON file that goes, from the country of India down to each province, down to cities and districts and streets. And Google Maps tends to put the latitude and longitude marker at the center of the most specific shape boundary that's encoded in the address. And so there is a chance that for addresses where nothing more specific than the word India could be found, it's going to place that marker at the sort of geographic center of India. And so there will be a bit of overrepresentation of firms at that point, and for each similar point for each province and so on. In general, I haven't found that this creates a particular skew because of that process we did earlier, where we took the longest string for the address that we could find. That being said, there are a few mistakes that Google Maps' API is just going to make. So you'll find some pins dropped outside of the geographic boundaries of India, in the wrong hemisphere or something like that. And so for those, I actually ended up just tossing every latitude and longitude coordinate that ended up outside the geographic boundaries of India. I want to note here on line 304, I make a note of this, that at one point I had implemented a k-means clustering algorithm to try to capture city-level clusters in latitude and longitude pairs to see if there was a way of improving the accuracy of the model by using, for instance, I think India had, when I was trying this, it said that there were maybe somewhere between 40 and 100 cities with a population of over 1 million people in India. And so I implemented a clustering algorithm using whatever number, you'll have to do a Google to figure out whatever number that is, to see if I could improve the accuracy of the model that way. And the answer was, it did not improve the accuracy of the model. It hurt it slightly, and it caused the model to run much more slowly because of the clustering step. And so ultimately I decided to take it back out and use just the latitude and longitude. And the machine learning algorithms that I use for this, like for instance, random forest is the machine learning algorithm that according to my head-to-head matchups works best in this instance. It allows two features to interact with each other. And so if there is an emergent property of risk that comes up at the city level, the random forest algorithm can allow for that. And I think that's another reason that the k-means clustering didn't improve the accuracy of the model at all, because the latitude and longitude data is enough information for the model to discover it if that's what's encoded in the data itself. I think we can just sort of breeze through the rest of the model building. Basically, it's taking the company name, the address, the authorized capital, paid up capital, trade partner count, and latitude and longitude labels as features. On line 309, all of the columns that are being selected to train the model are numeric columns. The algorithms that I'm using to test this typically don't allow for categorical data variables, for instance. There can't be variables that don't relate to each other in a scalar way. Like, for instance, the identity of the directors would be categorical data that we're just not capable of using at this level. I want to go through some decisions that I made preparing the data to be fed into the model by first pointing out that observations of forced labor at the firm level are extraordinarily rare. Even the best audit data recognizes a true case of forced labor between 1 in 10,000 and 1 in 15,000 audits. And we believe that the true occurrence of forced labor is actually much higher than that based on our prevalence studies that put it in risky industries around 5 to 8%. And so, if we didn't account for this imbalanced data, the model would just say, all firms are low risk, forced labor is not a problem. This machine will just tell you, everybody's low risk. But we know that's just not true. And so we have these two imbalanced classes of high risk for forced labor and unknown. And we need to make them more comparable so that the data gives us useful information. There are 3 ways I tried dealing with this imbalanced data. The first is downsampling. That means taking a small selection of the majority class and comparing it to the full data set in the minority class. The second is upsampling, which is duplicating the data in the minority class and using that to balance the 2 categories a little bit better. The third is called SMOTE, S-M-O-T-E, which is an algorithm that's used frequently in the field of credit card fraud. It models the data in multidimensional space. So if we have 5 training variables, then it would model the data in 5-dimensional space. And at each vector that connects any 2 points of the minority data in that space, it would place a synthetic data point at the midpoint of that vector. And so it's basically imputing more data points in the minority class. And it's computationally more expensive than either upsampling or downsampling. And I tried implementing it for this purpose, and it did not improve the accuracy of the model. And also it, again, caused the model to run slowly. So I felt like it wasn't worth it. It wasn't part of the most parsimonious model. And instead, the method that worked the best for me was downsampling. And so that's what I recommend doing if you're implementing this yourself. Here in this iteration, we downsample the majority class to about 100 lines. And I've set a seed for the 100 lines that are going to be selected. And if you're running this model on your own, you might want to take that out so that you get a good sample from your roughly 60,000 lines of data that this represents to be included in the majority class. But I've set the state so that people can replicate what I did exactly, and they're going to get the same results every time. The rest of this is a fairly straightforward implementation of an sklearn classifier. In this instance, I've got k-nearest neighbors as the classifier, but I have tried k-nearest neighbors, random forest, and the sklearn multi-layer perceptron, and in general, I get the best results with the random forest. So that's what I recommend. Although, depending on the data that you're working with and your goals for your model, you might want to use something else. I just tried a few things and gauged empirically which overall had the best accuracy and precision and computational performance, and I felt like random forest was the best for this use case. I think that brings us to the end of the model. You may, at the end, want to implement the metrics, including a classification report and a confusion matrix, and that will tell you how accurate and precise your model is performing on the data that you've incorporated into it. And so with that, I wish you best of luck. I hope you take this and run with it and make it much better than I ever could. And I look forward to seeing what any of you do with this work. It would be enormously gratifying to me if you implement a version of this model in any sort of industrial or scientific project. Give me a shout at my first name, Shannon, at gfems.org. Thanks. Bye-bye.